Hi there, Andy Warwick here with the second video on the origins of field theory. In this one I'm going to be looking at the work of the Scottish mathematician James Clerk Maxwell, who developed the first fully mathematical field theory, electromagnetism. And in doing so he conjured into being the largest object in the universe, one that we no longer think exists. So Maxwell was born in Edinburgh in 1831 and he grew up in the city and at his father's estate in Glenlair, around 100 miles southwest of Edinburgh. He was educated at home, then at the Edinburgh Academy. He was particularly interested in mathematics, publishing his first original paper in that field when he was just 14 years old on the mechanical construction of oval curves. The paper was read to the Royal Society of Edinburgh by James Forbes, who was Professor of Natural Philosophy at the university. In 1847, aged 16, Maxwell went to the university. He continued his studies in maths and he went to Forbes' lectures on natural philosophy. Forbes taught much of what we'd call the physics of that period. Scotland's education system, unlike England's, included advanced classes in natural science, covering some of the mathematical physics of the great Parisian theorists like Laplace and Fourier. Maxwell found the work easy, and back home in Glenlair he began experimenting on electricity and magnetism and investigated polarized light. He was the first to demonstrate photoelasticity, making mechanical stress and strain visible in polarized light. On the slide here you can see the young Maxwell with his famous colour wheel that he used to investigate colour vision. So Maxwell's quite unlike Faraday or Ørsted. He's well educated in the mathematical sciences of his day. He's a talented and original mathematician as well as an experimenter. And in 1850, aged just 19, he was sent to the home of British mathematics, Cambridge University, to study for the famous Cambridge mathematical tripos, perhaps the most grueling mathematical training in the world. In the early 19th century, Cambridge, like the École Polytechnique in Paris, pioneered a new kind of undergraduate study. Instead of the traditional fields of law, medicine and theology, the new studies focused on mathematics, in Cambridge's case especially Newton's mechanics and Euclid's geometry. And these studies required new kinds of training and examination. On the slide here you can see a traditional examination by oral disputation in Latin. This kind of examination was well suited to testing soldiers, statesmen, lawyers and clergymen, men for whom public speaking was really going to matter. The new studies in mathematics were quite different. They required small class teaching by professional tutors, or coaches as they were called, who used daily problem sets to be solved against the clock, new textbooks of advanced mathematical methods, and competitive written examinations. Now compare the public disputation with this rare depiction of a mathematics exam in Trinity College, Cambridge in the 1840s. The room is silent, policed by the tutors. The students solve problems on paper against the clock and are judged entirely by the marks they accrue. It's a new and very different kind of pedagogical economy. So here on the left is Maxwell's mathematics coach William Hopkins, perhaps the most influential mathematics teacher ever. In the middle, one of the new books of past tripos exam questions with solutions so students train themselves in the mathematical technique and problem solving. Here on the right, one of the new textbooks used to teach the physical subjects, in this case hydrodynamics. Each solution is followed by tripos questions to show how the theory is used to tackle real problems. And the author here, William Besant, was himself a wrangler, as the first class graduates were called. He was also himself a coach at St John's College in Cambridge, and he was a regular tripos examiner. So you can see how self-referential this new pedagogical economy in Cambridge actually was. This new world of competitive paper-based studies became the model for teaching technical disciplines, first in North America and Europe, and then globally. But it was new in the mid-19th century and was the vehicle for disseminating levels of technical skill that had previously been confined to professors and academicians. Maxwell joined these studies, but the competitive pressure led him to a mental breakdown and he had to leave the university for a while to recover his health. Nevertheless, in 1854, he graduated as second wrangler, the second highest scoring man of his year. And he went on to take the most advanced mathematical exam in the university, the Smith's Prize, tying for first place. Now, what Maxwell had and hadn't learned was really important. He had learned about fluid flow. On the left here you can see a page from Mazant's textbook where he's using a solved problem to teach advanced hydrodynamics. Down the bottom here he says this is a Senate House problem from 1847. Maxwell had also learned a lot of advanced calculus. In the Smith's Prize exam, for example, he was asked to prove an integral theorem that had yet to be published. The examiner, George Stokes, set the proof of what we will call Stokes' theorem as a question to the students. Maxwell mastered a number of theorems of this kind, the divergence theorem, Green's theorem and so on, and he would shortly put this to very powerful use. What hadn't Maxwell learned? In his time, physics meant things like celestial mechanics, optics and hydrodynamics, but new areas like thermodynamics and electromagnetics weren't studied in Cambridge because their theoretical foundations were thought to be insecure for a rigorous training. When he graduated, Maxwell became a Fellow of Trinity College in Cambridge, and he also wrote to Britain's leading physical scientist, William Thomson, later Lord Kelvin, asking about good areas for research. Thomson was also a Scot who'd learned natural philosophy in Scotland. He'd then gone to Cambridge, where he too was a student of Hopkins. He'd also been second wrangler, and he'd been a Smith's Prizeman. And Thomson was also the first mathematician to get interested in Faraday's field theory. What Thomson had done was to use Faraday's image of lines of force to apply the mathematics of heat theory to electro and magnetostatics. Just as heat flows in lines through a conducting medium, and remember Thomson initially thought heat was a fluid, caloric, so he imagined electromagnetostatic forces flowing along similar lines. Heat becomes charge, temperature becomes potential, and then you can apply the mathematics developed by Joseph Fourier in Paris. And the medium matters because Faraday had shown that if you change the dielectric between charged bodies, the forces change too. So the medium matters. It's likely Thomson recommended Maxwell to take this further by studying Faraday's papers to see if he could build a more complete mathematical theory of electromagnetism. And when Maxwell read Faraday's papers on electric and magnetic lines of force, he saw fluxes flowing in a hydrodynamical medium. Most fundamentally, he saw magnetism as a whirlpool or vortex motion. This was partly because magnetism always seemed to circulate, always formed closed loops, and because the lines of force rotated polarized light, so the lines must somehow rotate. From 1854 to 1862, Maxwell built an imaginary model of Faraday's force fields, which was part hydrodynamic and part mechanical. He used the model to find equations representing the physical state of the electric and magnetic forces in space. He published his ideas in 1861-62 in a paper entitled On Physical Lines of Force, in which he showed how he'd used analogies to turn Faraday's imagery into a mathematical theory. In figure 1, we can see how literally Maxwell initially took this hydrodynamical model. The current from a zinc and copper battery is represented by a flow of liquid around this loop of wire. The liquid causes a magnetic toroid to revolve on its own axis, and the resulting motion in the surrounding medium represents the north-south orientation of the magnetic poles. Maxwell used this imagery to write down his first equations of electromagnetism, and what he's struggling with is that even in this simplest case of a current-carrying wire, the physical problem is three-dimensional. And remember, vectors aren't used at this time, they came from this struggle. Now Maxwell wanted a clearer idea of what was happening on a micro level around a current-carrying wire. And this prompted him to invent his most famous mechanical model. And you can see that model here in figure 2. He described the model as a provisional and temporary hypothesis, and during 1861-62 he used it to make an extremely important contribution to theoretical physics. So what is this model? You have to imagine that the whole universe is filled with an electromagnetic mechanism or ether. Maxwell says that each of these cells, as he calls them, is probably smaller than a molecule. And note this is a two-dimensional model, whereas the equations taken from it have to be written in 3 dimensions, even though the model wouldn't then work. So rather like Faraday with his lines of force, Maxwell is using this model as a heuristic device. Now Maxwell tells us, I've given you part of the text down here, why the model is like this. He thinks magnetism is a kind of rotation, but he says he found great difficulty, quote, conceiving of the existence of vortices in a medium side by side revolving in the same direction. The problem is that if they revolve the same way, they'll rub against each other. So he says, the hypothesis he made, quote, is that a layer of particles acting as idle wheels is interposed between each vortex and the next, so that each vortex has a tendency to make the neighbouring vortices revolve in the same direction with itself. In other words, if this vortex is revolving around like this, these little idle wheels will turn in the middle so that this vortex revolves the same way as this one. Maxwell asks us to see each of the hexagons as a kind of elastic cell so that it can revolve even though it's hexagonal. And he points out that the calculations he's making, like calculating the angular momentum of the cell, aren't changed much by its surface shape. When a cell spins, it represents a magnetic field. The cell turns the idle balls, which turn the next cell, and so the magnetic field slowly travels outwards. So how does an electric current actually make a magnetic field on Maxwell's model? Well, outside of a conductor, the little elastic balls or idle wheels are fixed in the sense that they can't move, they can only rotate. But inside a conductor, the little balls can actually move along. So here in the diagram, these balls are coming in at A, this is supposed to be a conductor, they are moving through and they're leaving here at B. And as they move, they set the hexagons above rotating one way and the hexagons below rotating the other. And this positive is one polarity of magnetism and this negative sign here is the opposite polarity. So you have to imagine these hexagons forming a kind of toroid around a current carrying wire. Treating the cells and balls in terms of angular momentum and energy, Maxwell wrote down an equation for the magnetic field H surrounding a current carrying wire. And here he frequently made use of integral theorems because these kinds of mechanical analogies are often much easier to understand intuitively in terms of integral forms. So here on this slide we can see Maxwell's differential equation for the magnetic field H around a current J in our vector notation. And now we come to the really important point. Maxwell wanted the model to include electrostatic force, but how was he going to do it? What he said was that like the hexagonal cells here, the idle wheels or balls aren't solid, but they're also elastic, so they can distort and take on a strain in the medium. This displacement, as he called it, is electrostatic charge. It begins on one charged body and communicates it across space to other charged bodies. Now suppose we imagine two capacitor plates being charged by a battery. We can imagine the current flowing from one plate through the battery round to the other plate. But what about the space between the plates? How is the electrostatic force communicated? Maxwell said that it wasn't instantaneously by action at a distance as on a Newtonian model, but rather we have to imagine these little elastic balls gradually and sequentially distorting to carry the strain across the space. And Maxwell called this a displacement current that completes the circuit between the battery's poles. And now we come to the really important point. This brief displacement current also moves the hexagons. This means that there is a brief magnetic field between the plates. And in that case, we have to add the displacement current to our equation here. But this makes a crucial difference to Maxwell's scheme, because now electromagnetic effects can propagate like a vibration through the elastic medium. Maxwell calculated mechanically how fast this vibration would travel, and the answer came out very close to the velocity of light. And so Maxwell concluded, and I quote, "We can scarcely avoid the inference that light consists in the transverse undulation of the same medium which is the cause of electric and magnetic phenomena." So just as Faraday had speculated that light was a vibration in his lines of force, Maxwell had now united electromagnetism and light. Here's the full set of equations Maxwell derived from the model over here on the left in the form he gave them, here on the right in our vector notation as given by Oliver Heaviside. Down the bottom here I've noted how Stokes' theorem is extremely useful in allowing Maxwell to move between integral and differential forms of his equation. In Maxwell's next paper of 1865, he abandoned physical models and noted how equations 3 and 4 yield a self-sustaining transverse wave, as you can see in these equations here. He now made the ether a dynamical medium in which the new notion of energy was conserved. In speaking of the energy of the field, he said, "I wish to be understood literally. All energy is the same as mechanical energy." So the ether is now mechanical, but we don't know its mechanism. In 1879, the year Maxwell died at the young age of 48, he wrote, and I quote, "Whatever difficulties we may have in forming a consistent idea of the constitution of the ether, there can be no doubt that the interstellar spaces are not empty, but are occupied by a material substance or body, which is certainly the largest and probably the most uniform of which we have any knowledge." In the 1880s and 90s, Maxwell's field theory became a big research project in both theory and experiment. In 1883, for example, the Cambridge Wrangler John Henry Poynting investigated the way energy moves around a current-carrying wire. In doing so, he found the Poynting vector and discovered that energy flows from the field into the wire. So all the interesting physics wasn't now happening in batteries and wires, but rather in the space around them. In 1888, the German physicist Heinrich Hertz succeeded in experimentally generating and detecting electromagnetic waves. Physicists now realized that electromagnetic waves weren't confined to light, but were generated by any accelerating charge. In the 1890s, physicists studied the theory of rapidly moving electric and magnetic bodies. This was an important problem. If electromagnetic effects were due to an ether, then the Earth must be travelling through it extremely rapidly. Why were no effects of this motion experimentally detectable? In 1905, the 26-year-old Albert Einstein offered a radical solution to this problem, but it wasn't his work that he saw as revolutionary. In 1931, Einstein wrote, and I quote, "The greatest alteration in the axiomatic basis of physics since the foundation of theoretical physics by Newton originated in the researches of Faraday and Maxwell on electromagnetism." The field theory developed by Faraday and Maxwell offered a new way of thinking about physical phenomena that was radically different from Newton's action at a distance model. In Einstein's view, his own special theory of relativity merely completed Maxwell's work by showing how the equations were valid in any inertial frame of reference. Einstein retained the field while dismissing the material ether as superfluous. And of course, Einstein went on to develop his own field theory of gravitation in the form of the general theory of relativity. So why have I called this a cultural or constructivist history? I've described the work of Ørsted, Faraday and Maxwell in terms of their upbringing, their training, their motivation and the resources available to them. Ørsted drew upon his training as a pharmacist and on the German philosophical tradition. Faraday on the laboratory and maritime mapping resources of metropolitan London. Maxwell on the training in higher mathematics available in mid-Victorian Cambridge. So my account is naturalistic, probably because my original training was in science. That is, I'm interested not in how science should or ought to be done, as idealized in some philosophical accounts of science, but rather in how it actually was and is undertaken. And to me, that's important in locating natural knowledge in its cultural time and space. We can't know what ultimate goals or truths science might reach, only the cultural conditions that make them imaginable and plausible. Thanks for watching.